Welcome to Limits Involving Infinity Part 2, where we will discuss the end behavior of rational functions. First off, I didn't even write this, but there's a lot of prereq info. The first prereq info I want us to understand is that a rational function is one that has x, or whatever the input variable is, in the denominator. Therefore, there is some sort of value that makes our denominator 0 most of the time, and therefore we will have a vertical asymptote. And then what is end behavior? End behavior is how a graph behaves at the ends. So as we look all the way to the right and all the way to the left, those are the ends of the graph. And I say end behavior here, and I really mean if it's going towards a number, like in this case, this graph is approaching y equals 1, that is a horizontal asymptote. So end behavior a lot of times will be a horizontal asymptote, but we'll also see that the graph might shoot off towards infinity at the end, and that is not an asymptote. So end behavior is a larger catch-all phrase to possibly describe the presence of a horizontal asymptote. So right end behavior is how the graph behaves all the way to the right as x gets very large or approaches infinity. So the way that we write the right end behavior, and let's call this graph f of x, the way that we write right end behavior is it is the limit as x approaches infinity of our function. Now, in this specific graph, which I'm calling f of x, the right end behavior, as x gets very, very large, we can clearly see that our graph is approaching where y is 1. So that is just for this example, so I'll write in green, that this right end behavior happens to be 1. But overall, in pink, right end behavior is the limit as x gets very large, what's happening to the right of the graph. The left end behavior is very similar, except we're looking left in this case, and so the left end behavior is as x gets very small, as we look literally to the left towards the negatives. So it's the limit as x approaches negative infinity of our function, and almost in all cases, again, I say almost, but in almost all cases, they're going to be the same. Note that the right and the left end behavior of f of x here is both 1. Even though our function's approaching the horizontal asymptote y equals 1, here from the top and here from the bottom of it, doesn't matter, they're both 1 in this case. So this is how we write right end behavior. It's a limit as x goes to infinity. The way we write left end behavior is the limit as x goes to negative infinity. And in this specific example, they both happen to be 1 because we have a horizontal asymptote y equals 1. Now, in order to figure out the end behavior of any rational function, we do have to know just two quick things that will be in the rules for this in just a moment. So we need to make sure we understand what degree of a function is and what the lead coefficient of a function is. Okay, so for this cubic function here, this cubic trinomial, the degree is what the highest exponent is. So our degree here is 3 because it's a cubic function. So in this problem, in this function, not a problem, the degree is 3 because it's a cubic function, and the lead coefficient is going to be the number that is out front in that term. So like this is our leading term, not just because it's first, but because it is the term that has the largest exponent, and a lot of times if it's written in standard form, it will be written first, but so the lead coefficient here would be 5. And I will abbreviate lead coefficient as LC, and it's 5. Okay, for this example here, g of x, we have a quartic binomial, 2 terms, and we can see that our degree here is actually 4, right? This is not written in standard form because this term should be written first if it was written in standard form. So I did this example just to show you here that the degree is 4, it's the highest exponent. And then our lead coefficient is the number out in front of that term, which is -2. Okay, for this example here, I have a rational function with both a numerator and a denominator, and so I'm going to split that up. So we'll first look at the numerator, because this is how we'll deal with these problems. So in the numerator, the degree, I don't see an exponent there, It's just a constant, so that is degree 0. You technically could write 3x to the 0 since x to the 0 is just 1, but that is degree 0. And then the lead coefficient in the numerator is 3. Now for our denominator, our degree in the denominator is 2, since it's a quadratic down there. So our degree is 2 in the denominator, and the lead coefficient is the number out in front of that, which is just a 1. So when we do have fractions, which we will have for rational functions, we will split it up by finding the degree and lead coefficient of both the numerator and the denominator. So that is our quick review. Let's get into the rules for end behavior of rational functions. All right, now this can look a little bit overwhelming. This says to find the horizontal asymptote, we compare the degree of the numerator with the degree of the denominator. So we have our rational function here, f of x, and we can clearly see that instead of numbers out in front, they are generically calling those lead coefficients a and b. And instead of having numbers here in the exponent, they're generically calling the degrees n and m. So we will say that n, that is the degree of the numerator, and m, that is the degree of the denominator. And then if we look at what a and b represent, a represents the lead coefficient of our numerator, whereas b represents the lead coefficient of the denominator. All right, so we have three different things, looking at the degrees mainly. If the degree of the numerator is less than the degree of the denominator, if the two degrees are equal, or if the degree of the numerator is greater than the degree of the denominator. Those are the only three options. In the first case, our horizontal asymptote is y equals 0. In the second case, if they're equal, we also have a horizontal asymptote. It's the ratio of the two lead coefficients, just a over b. And in the third case, if n is greater than m, then there's no horizontal asymptote. Don't worry about the oblique asymptote. That just means our function is not bounded by a horizontal asymptote. It shoots off towards infinity. So please make sure you have these three rules written down, and we'll get into some examples to find the horizontal asymptote or say that there is none. Okay, we want to find the horizontal asymptotes if there are any for each of these functions. So what we need to do is find out what n and m are. So n is the degree of the numerator, m is the degree of the denominator. Let's write those out. So n in this case is the degree of the numerator. 1 is just our numerator, so that's degree 0, because it's just a constant. And the degree of the denominator, m, is 2. So let's see what situation we have. We have that n is less than m. That means we have a horizontal asymptote, this graph. This graph approaches the horizontal asymptote y equals 0. So in this case, this horizontal asymptote, which I'll call HA, this horizontal asymptote is the line y equals 0. That means the end behavior of this graph, all the way to the left and the right of the graph approaches the x-axis, the line y equals 0. And we'll explore that graph in just a minute. Okay, let's take a look at number 2. Let's find n and m. So the degree of our numerator is 3, and the degree of our denominator is also 3. That means we have the second case. They're equal. We also have a horizontal asymptote here, and this one is specific to this function because it is the ratio of the leading coefficients, a over b. Our lead coefficient here is 4, and our lead coefficient down here is 10. That means the horizontal asymptote is the horizontal line y equals 4/10, which is y equals 2/5. That means on both ends of our graph, our function levels out and approaches the horizontal line y equals 2/5. Okay, let's just take a look at this graph of f of x. We're claiming that the horizontal asymptote is the x-axis, the line y equals 0. So I graphed it on Desmos. We graphed that function, and it's a weird looking function, but if we do zoom out a little bit, oops, if we're able to zoom out a little bit, we can clearly see that our right end behavior, our graph is approaching the x-axis, the line y equals 0, and our left end behavior, as x approaches negative infinity, our graph is also approaching that same line, y equals 0. So y equals 0 is our horizontal asymptote, and we can like zoom really far and see it never touches y equals 0. It approaches it, and therefore that is our horizontal asymptote. For these next two examples, go ahead and try answering them on your own. Go ahead and pause the video and then hit play to see how you did. All right, so for number 3, we have no horizontal asymptote because n is larger than m. And for number 4, our horizontal asymptote is the x-axis, aka the line y equals 0, because n is less than m. Let's take a look at the graph of number 3, this kind of weird function that I just made up. So I do want to show you that this graph here, as we look at it all the way to the right, if we look at the right end behavior, our function is not bounded by any horizontal line. I say not bounded because it's like you can't hold it back, right? You can't tell this graph what to do. So instead, it's shooting off towards positive infinity all the way to the right. It actually has an oblique asymptote, oblique just meaning diagonal, but we're not going to worry about that. And then if we look to the left, it also is not bounded by any horizontal line in the same way. So that's why we would say this type of graph here, this rational function, does not have any horizontal asymptotes. And that is the end of this video. Part 2, finding the end behavior, aka the horizontal asymptotes, if there are any, of rational functions using these 3 handy-dandy rules.